All right, everyone, this week we're going to talk about the Earth, primarily the way the Earth moves around the sun and the way the Earth moves in general, how we locate different points on the Earth, and then we'll talk some about the moon. So, the movement of the Earth through space is what causes us to experience the way life is on Earth. Right? So, the Earth is tilted. So, when we're at different points around the sun, we experience different seasons. When we rotate, we experience night and day at different times or for different amounts of time depending on where we are around the sun. So everything that we experience on the surface of the Earth goes back to how the Earth moves around the sun and how just the Earth moves in general. The Earth itself is what we call an oblate spheroid. So it's basically like a basketball if you squished it down. It's basically a little bulgy towards the center and a little skinnier towards the top. Now there are three motions of the Earth that are independent of the sun and everything else that's going on. Now we move around the sun and the sun moves, but our motion is independent of those. One is the yearly revolution around the sun, the Earth in its orbit going around the sun. The second is the Earth rotating on its axis. And then the third is a clockwise wobble of the rotation axis. The third one is the one that people don't know a lot about, and we'll talk about that with a little bit of detail. So first, let's just talk about the Earth going around the sun. The Earth's orbit around the sun is in a particular plane. Most of the solar system is relatively flat in that plane. The further out planets are a little more inclined, but most of it's relatively flat, but we're not worried about everybody else, just us. And the way that we see the sun as it moves through the sky creates a path. Now that path changes over time, but that path is referred to as the ecliptic. It is the apparent path of the sun as it moves through the heavens on Earth. Now, depending on where you are and how you observe that, you're going to see the sun move in a different place. Now, the Earth's orbit is elliptical. It's not circular. So it's a little bit closer in January than it is in July. Even though it is summer here in July, we are a little further away from the sun. And the distance is not that significant. The Earth receives about 6% more solar energy in January than it does in July. So as you can see here, this is essentially a map of the orbits of the inner planets. And the Earth's orbit is mostly circular. It's hard to tell that that's any different from a circle. Venus, also hard to tell that it's any different from a circle. You can see that Mercury, the sun, does not sit at what would be the center of Mercury's orbit if Mercury's orbit was a circle. Mercury's orbit is more elliptical than Earth and Venus for sure. You can see kind of the same type of elliptical shape with Mars. They're still close to circles, but they're not circles. Now, in terms of the Earth rotating, the Earth is tilted. It's inclined 23.5 degrees to its particular axis. So instead of being straight up and down, it's basically tilted at 23.5 degrees, and we rotate at that angle. The seasons that we experience are determined by our orientation with respect to that tilt, whether we're tilted towards the sun or whether we're tilted away from the sun. When you're tilted towards the sun, then you're experiencing summer. When you're tilted away from the sun, you're experiencing winter. Now, as we talked about in a previous chapter, we basically take what we call the celestial equator. Okay, so that is the line in the sky that sits above the equator on Earth. And notice that it's inclined 23.5 degrees to what would be the ecliptic, the path that the sun takes as it crosses across the sky. And so, if it's inclined to that particular angle, at 2 points along this path, these two things meet. The first is in the spring, and the second is in the autumn or the fall. We refer to these as the spring equinox, or the vernal equinox, and the autumnal equinox, or just the fall equinox. The points where you are furthest away, where those two paths are most separated, referred to as solstices. And we have over here we have the winter solstice and the summer solstice. You will see what all of this stuff means in terms of their names and things in just a moment. So this is more what the Earth looks like as it's going around the sun. And just for the sake of having a place to start, we're going to start when the north hemisphere is in spring. So on or around March 21st, we have what's known as the spring equinox or the vernal equinox. At that point, you have equal times of daylight and darkness. Equinox means equal night, but what it really means is we have equal night and equal day. As you move on from spring, if you'll notice, there's a couple of things that you can see. First of all, you'll notice that days start to get longer, longer and longer and longer. The sun will start to stay up well past 8 o'clock at some points as you approach the middle of June. Also, if you pay attention, you'll notice that the sun starts to get higher and higher in the sky throughout this time as you go from spring on from March on into June. When you reach what's known as the summer solstice in the northern hemisphere, it is summer in the northern hemisphere in June. It is winter in the southern hemisphere. Winter because they are tilted away from the sun. Summer because we're tilted towards the sun. And at this point on what's known as the summer solstice, you have the longest day of the year, the most hours of daylight. As the Earth rotates, you spend a longer amount of time in this space, so you spend a longer amount of time illuminated by the sun, so you have the longest day of the year. As we move from the summer solstice towards autumn, towards fall, you start to notice that days will get shorter and shorter and shorter, up until the point where you reach September 23rd, which is known as the autumnal equinox or the fall equinox, when we have again equal parts daytime and nighttime. You'll also notice, if you pay attention, that the sun starts to move lower and lower and lower in the sky. Think about what the sun looks like at noon in June or July, and then think about what the sun looks like at noon now or around the middle of October. It's much lower to the sky. Once we reach this point of the equinox, notice when we are passing through these points at the equinoxes, the tilt of the Earth is essentially perpendicular to the sunlight. So the tilt doesn't affect the season as much, and it exactly doesn't affect the amount of daytime or nighttime. And so you have exactly the same amount. As you move from autumn on into winter, days become shorter and shorter and shorter and shorter and shorter. As you notice, the sun will start to go down around 6 or 6:30. If you look at the sun at noon, you'll notice that it's just barely above the horizon, up until the point where you reach the winter solstice, which is the shortest day of the year, and by far the most amount of nighttime. We in the northern hemisphere are tilted away from the sun at that point, so we spend more time in this darker region than we do in the lighter region. And so at those points, we have the shortest day of the year. As we go from the winter solstice on back to spring, days become longer and longer and longer again, until at the point of the equinox in spring, they're equal, and then the pattern repeats. Just a few important things to point out. The seasons come about from the tilt of the Earth, whether you are tilted towards the Earth or away. Summer when you're tilted towards, winter when you're tilted away. It does not depend on the distance. We are closer to the sun in the winter than we are in the summer. It may be a little tough to see in this picture, but it's there. There's a slight difference between the two. Now, if you were to observe the Earth move around the sun from space, you would notice that the sun moves through space like other stars, and the Earth would essentially generate a helix, orbiting around the sun as it moved forward. There's evidence for the Earth rotating. You can't experience it, aside from the fact that you can watch the sun, and you know that day and night over time. But we can see other celestial bodies that rotate. Jupiter rotates. The sun rotates. We can use what's called a Foucault pendulum, which is basically just a pendulum that oscillates in a fixed direction due to the Earth's rotation. And you can see an example of this if you were to take a pendulum and just spin it on a chair. As this spins, the pendulum will oscillate back and forth. You see the same thing with the Foucault pendulum on Earth. And then we also see what's the Coriolis effect, which is the deflection of winds as the Earth rotates. Causes them to kind of spin up and form circles. One thing that I want to point out that's a common misconception is that the Coriolis effect causes toilets in the southern hemisphere in Australia to flush in the opposite direction. That is not at all true. They all flush in pretty much the same direction. And I will try to include a video that will show you that. So this is just a picture of the sun rotating, right? We can see that the sun also rotates. You can see the sunspots move across it. And here you can see about how big the Earth is compared to the sun itself. Now the third motion of the Earth is the one that's more interesting, and it's the one that you definitely don't notice, but will have an impact over time. So it's what's known as precession. And the way to think about precession is to think about what happens as you have a top that's spinning really fast. And then as that top starts to slow down, what happens to it? Right before it falls over on its side, it'll start to wobble some. It'll no longer be standing straight up and down. And as it wobbles, it's still rotating. And so you get this kind of shape of a cone that it forms. Well, the Earth is very similar. The Earth was spinning much, much faster millions and millions of years ago. And as it's slowing down, and it's tilted on our axis, as it's slowing down, it precesses. It wobbles like a top. And so the axis of the Earth is much like the axis of this top. Over a significant period of time, that axis will rotate and form somewhat of a cone shape, so that what is now our North Star today, in about 12,000 years, will be pointed in the opposite direction. About 13,000 years later, you'll be pointed back in the same direction that we are today. It takes about 26,000 years for this one precession. But when you're on the opposite side of it, so every 13,000 years, you'll be tilted in the opposite direction. So seasons will change, so that those in the northern hemisphere would experience summer in December and winter in July. You wouldn't notice this as humans, as a single individual living, but as a society you could. 14,000 years would be recognizable. The other interesting part about this is that this precession, of course, has been going on for a long time. And though many people believe in the idea of the zodiac and astrology, if you base your zodiac sign on whatever the dates they're giving you are, those dates were set a long time ago, hundreds and hundreds of years ago, based on the position of the sun and the earth and the way that we view the stars. I don't know exactly how they determined where the dates were and all those things, because I don't know that much about astrology, because it's not a real science. However, because of the precession of the earth, when those dates were set for your zodiac sign, and now when you were born, the sun has actually moved. There's a very good chance that your zodiac sign is not the same as where the sun was located when you were born, which is the whole idea behind it. It's advanced by about 2 or 3 weeks. So if you're at the very early point of one of them, then you might still be at the end. But if you're anywhere in the middle, it's the one after it, I think. I'm not sure. But astrology is meaningless due to the precession of the earth, because the dates they give you are not the same as they are now if you still base it on the position of the sun when you're born. So the Earth's revolution around the sun and the Earth's rotation about its axis allow us to get an idea of places and times, and allows us to establish some way to measure time on the Earth for ourselves, so that we have some kind of way to exist. The first thing we have to do, though, is we have to be able to understand how to locate a place on the Earth itself. So if you have a flat 2D surface, well, you can just draw 2 straight lines and that 2D surface will meet right where you need it to. But that doesn't work when you have a sphere, when you're all living on a sphere. Straight lines between 2 places doesn't connect. So if we want to instead map out what the surface of the Earth would look like, we use 2 different types of lines. The first are what are known as parallels, and these run parallel to the equator. They run west to east, but we use them to measure north and south. So 10, 20, 30 degrees is about the Gulf Coast where I live, and so on. From 0 to the bottom we go down, and it goes negative 20, -40, or 20 degrees south, 40 degrees south, until we get to 90 at the South Pole. When we want to go east and west, we use lines that run north to south, and we call these meridians. The prime meridian runs through a particular place in England, and we measure directions west of that all the way around to the international date line, which is out in the middle of the Pacific Ocean, off the east coast of Australia. And then we measure from England all the way around the other way to the date line. The west direction is negative, the east direction is positive, or we just say 90 degrees west or 50 degrees east. And so using these sets of parallels and meridians, we can then map out the surface of the Earth. Now, there are some parallels that are of particular importance. First of all, let's just start with the equator. The equator is the 0-degree parallel. If you look at this image, you'll notice that this line is always half in the dark and half in the light, no matter whether you're over here, right, tilted away from the sun during what would be our winter, or whether you're over here tilted towards the sun during what would be our summer. The equator has equal parts day and night. You would experience it just a little bit differently, because when the sun reaches close to the horizon, it appears that it's coming up, and that point would change some over the course of a year. So you would see sunrise as it would feel like it was a little earlier or a little later, but it's not going to be that big of a variation. As we move upward, you come to the next parallel, which is called the Tropic of Cancer. This parallel is at 23.5 degrees north, and then as you move further up, you reach the parallel which marks out the Arctic Circle. As you go down, the Tropic of Capricorn, which is at negative 23.5 degrees or 3.5 degrees south. And then as you go further south, you come across the Antarctic Circle. One other thing I do want to point out here is that if you live in the Arctic Circle, then when it is summertime, your line of latitude never leaves the shaded part, or this shaded part, the lightened part of the Earth. It's always in the sunlight. As you tilt it away, it's always in darkness. So those who live north of the Arctic Circle find that they get what is essentially 6 months of daylight and 6 months of darkness. That does not mean it takes 6 months for the sun to go from sunrise to sunset. What that means is that instead of the sun setting each night, it gets close to the horizon but doesn't go all the way down. It'll get closer and closer to the horizon, but it'll never go all the way down. And then finally, as you cross over from day to night, the sun will finally set. And then it'll be nighttime. And then the sun will never quite make it over the horizon. It'll get closer and closer, but never quite make it. Until one day it finally crosses over the horizon and it's daytime again. So you would still have a light cycle. It would still appear to be brighter and dimmer at certain times, but the sun would never fully go down below the horizon. Now, we use time standards to measure different intervals of time on Earth. One example is the rotation of the Earth, which is what we use to measure days, months, seasons, years. We also use the revolution of the Earth around the sun to measure those things. So first, let's just get an idea of what the Earth and the sun look like when they move beside each other, particularly what the Earth looks like as it moves around the sun. So we know that in a single day the Earth rotates, and we also know that the Earth goes around the sun over time. So over the course of a single day, the Earth will rotate, and as it rotates, it'll move to some other point in its orbit. Okay, the Earth rotates counterclockwise around the sun, and it revolves counterclockwise in the same direction. So it rotates and moves in this direction. When we view the sun on Earth, this is why the sun appears to rise in the east and set in the west. Now, in terms of what we call noon, noon implies that it is the point where the sun is at the highest point in the sky above you. Okay, it's referring to that it is over whatever your meridian is on the surface of the Earth. So we call that apparent local noon. That'd be at a particular longitude. What you would call noon would be the point where the sun is at the highest in the sky. After noon is when it starts to set. Now, we could use what is known as the apparent local solar time, which is basically measuring off of the position of the sun in the sky. You could measure this with a sundial, but this is not going to give you the same time that we measure with our clocks. Not everybody would necessarily measure the same thing. Sundial's a little outdated, so we use a slightly different way of doing it. Instead, we use what's known as the mean solar time, which is averaged over the orbital speed as the Earth goes around the sun and how the sun moves through the ecliptic over the equator. And what that leads to is we have a mean solar day of 24-hour average. What we call one single day is the amount of time that it takes for the Earth to rotate once on its axis. But again, there are different ways that we can measure a day. The sidereal day is the interval of time from when you can draw a line between a fixed point on Earth and some star out in space. One sidereal day would be when you've gone all the way around and gotten back to that point. Now, this amount of time doesn't vary that much. It's one essential complete rotation of the Earth. And the Earth rotates at a relatively constant rate. It is slowing down over time, but it's not noticeable, and that slowdown is going to take millions and millions and millions of years. So what we use as the apparent solar day is when the interval of time between two consecutive crossings of the celestial meridian by the sun, which that means 2 apparent times of noon passing one another. It's about 4 minutes longer than a sidereal day, and it counts to about 23 hours, 56 minutes, and 4 seconds. So because of the rotation of the Earth as it moves around the sun, and the different ways that we can measure days, because the Earth speeds up and slows down as it goes around the sun because it's closer at some points and further away at other points, the way that you would measure time based on the sun, or the way the sun moves across the sky, is going to change over time. If you were using a sundial to measure the sun, you're going to be off over time. And we know that as humans, as we exist, we have to have some kind of way of standardizing our time. So we use what are known as time zones. Those time zones take the 360 degrees of longitude, so 180 degrees, or 0 to 180 west, 0 to 180 east, 360 degrees, and divide it into 24 15-degree time zones. And then we adjust what those boundaries are based on where people live. So this is why you see that sometimes time zones occur across state lines, and sometimes they just occur in the middle of states. Some states use daylight savings time and allow to adjust for more daylight or darkness. And then you have what is the international date line, which marks the change between one day and another. And so each of these 24 time zones correlate with 1 hour time differences on the Earth. In the United States, we have 4 different time zones. We're in the Central Time Zone. There's also Mountain Pacific, and then Eastern. If you've ever been or stayed in any of these other time zones for a significant amount of time, you'll notice that the sun behaves differently, especially if you stick to your old clock and don't change the clock when you get there. I'm going to include this image in with your notes, but it's just an image of all the time zones in the world. It's just interesting to look at if you want to look at it closer. So the way we measure a year can be different in the same way that we measure a day. A tropical year is the amount of time between 2 spring equinoxes, and that amounts to about 365.25 mean solar days. So what that means is that every 4 years we have to add an extra day. And we add that extra day and call it a leap year. And that leap year accounts for the 0.25 that we see, and we can then essentially reset it. Now, there are some other things that cause changes to the way we observe spring equinoxes. So if something else were to slow down the Earth just a little bit, or if the Earth's slowed down the Earth just a little bit. And if you go back and look a few years ago, we actually had to have a leap second. We added 1 second to 1 minute, one night. I don't even remember when it was. I think it was 2015. Just tossed a leap second on there to just extend our clocks to match better with what the sun was doing. Similarly, we can talk about a month being measured as how the moon moves around the Earth, and the moon moves around the Earth very similarly to how the Earth moves around the sun. If we measure the sidereal month of the moon, the amount of time it takes for it to rotate and get back to where the same face is showing to the stars, then that takes about 27 1/3 days. If we instead measure the amount of time between consecutive phases, then we get about 29.5 days, and this is about the time that we usually refer to as a month, 30, 31 days, thereabouts. You'll notice that the moon will go through its phases about once a month, And then every once in a blue moon, you'll get a full moon twice in a single month.